Hello everyone. All right, we are back. There we go. Okay, we're back. So I am doing 8.5. My initial slide isn't showing right now, but just so those of you that are keeping up, I did 8.1, 8.2, and 8.3. 8.2 I took down because there's some tech issues with it, and I will figure that out, but I'm going to keep rolling right now. And then from 8.3, I'm going to do 8.5 and 7 because they're going to go together. And then after that, I'll go back and do 4 and 6. There is a method to the madness, I promise. And then we'll finish up with the last few. All right, so we're getting into titrations, and I want you to understand that titrations are massively big on the AP exam. The math that goes with them, reading the graphs, kind of understanding the lab procedure. And so I know it's like a video of a video. It's kind of boring, but I made this one super fast. Well, I didn't make it, but I picked this one because it's super fast just to give you kind of an idea a little bit. If I can get it to play, I'll give you a little bit of an idea of what a titration is so you can kind of understand what's happening. All right, so we're going to run through it really quick, and then when I'm talking through the stuff today, it might help you a little bit. All right, so let's just look. All right, so I'm pausing right here for just a second. I want you to pay attention to, when I'm going to be referring to it later, what he is holding in his hand at the bottom. That's the flask. That's the Erlenmeyer flask. And then what... It won't let me back it up. Can't back it up. But the long cylindrical thing, they call it a burette. So just pay attention to the vocabulary. We have the flask down here and we have the burette right here, because that's going to be helpful to us when we are talking about this in just a second. All right, so here's an even better view. We have the flask and we have the burette right here. And then this is just a ring stand that holds it up. All right, so let's move on. So now that we've kind of talked a little bit about what in the heck a titration is, so you kind of have a little bit of an idea. Titration are a way for you to quantitatively analyze acid-base reactions. So we can do some math once we're done doing the actual lab. Now, the reason why we do a titration is when we have an acid or a base and the concentration is unknown. So if we have an acid or a base and we don't know what the concentration is, then we can run a titration to figure that out. And so that's really important. So that's typically why we do it. And it doesn't matter which one's unknown. That's irrelevant. We can do either one, and we'll flip them around. So the volume of both solutions is measured so that you will know the volume of the acid and you'll know the volume of the base for sure. You're going to have an unknown concentration of one of them, and the other one you will need to know its concentration when you start. And then when you do that, that makes your life a lot easier. There's a couple ways to do the math that's involved. The math that I typically prefer to keep up with is M1V1 equals the M2V2, which is our Voom-Voom equation, right? That we use when we're changing volume and dilution. This also works here for titrations, and we'll talk about that in just a second when we get to it. But that one is an awesome one to use. I like that one the best over the stoichiometry method. That's just my thing. So that's one. Now, there are two vocabulary words something happened. Let me go back. There we go. There's 2 vocabulary words that you need to know, and one of them is the titrant, and the other one is the analyte. Okay, the titrant is the solution with the known concentration. That's the titrant. That's the one we know the concentration of it. Obviously, we're going to know the volume that we add of that once we get to the end. The substance that we're trying to figure out, the one we are analyzing because we don't know its concentration, that's the analyte. All right, so the titrant is the one that we know. We are titrating with it because we know its concentration, and then we can do some math later. And the analyte is the one we are going to analyze, and analyze means that is discussing how we're going to figure out what it is. We're going to analyze it. And so those are some vocabulary words that are super important that you have straight moving into this as well. And I want to show you guys one thing before we get any further into what we're doing. I'm going to take a little sidebar, basic acid-base information that we haven't talked about yet. Because up until this point, our acids and bases, for the most part, will have an acid and we dilute it or something like that. And then we'll mix it with another acid and that type of thing. Or we'll have a base and we dilute it. Great. Now we're going to be mixing them together. And acid-base reactions are called neutralization reactions. Not dilution, neutralization reactions. And so if you have an acid plus a base, so this is new for us because we haven't talked a whole lot about this. So we have acid plus a base. Then what you end up getting is you get a salt plus water. Okay, so acid and a base, you get salt plus water. You need to know this. There are several things that you need to know about this. So this is really important that you are keeping up with what the heck is going on in the acid-base reaction. And this is a neutralization reaction. It's also a double replacement. Whoa, that's a D. It's supposed to be a D. Double replacement reaction. Now we have a couple of different options that we can end up having. Okay, so we can have a strong acid and a strong base. And that's going to give us a salt plus water. And I'm not going to say anything else about what the significance of that and some things that you can figure out with that because there's quite a bit. We'll hang on to it. We can have a strong acid and a weak base. We're still going to get a salt plus water. All right, so now I'm going to flip them. I can have a weak acid and I have a strong base, and that's going to still give me a salt plus water. Okay, we're getting somewhere. Now, weak acids plus weak base, I could have that one too. And then we'll have a salt plus water. Okay, so one thing I want to talk to you about is the pH, because we tend to talk about pH when we're dealing with acids and bases. So if you have a strong acid and a strong base and you mix them together in a neutralization reaction, then what you end up with is you end up with a neutral pH. So the pH is usually around 7. It's going to be, depending on who it is. Strong acid, strong base, pH is going to be 7. Some of these other ones with the neutral pH, when they say neutral, there's like a little bit of a neutral range. But we're talking about for a strong acid and a strong base, that neutral is 7. The pH should be right at 7. That's exactly where it should be. Now, if I have a strong acid plus a weak base, then what that's telling me is that my pH is going to be on the acidic side. So the pH should be less than 7. If I have a weak acid and a strong base, then my strong base means that my pH should be around or greater than 7. And weak acid and weak bases, that's depends on who they are. And so then you're going to have to look at their Ka values and Kb values. It depends on how strong because remember there's a big range. There could be all kinds of things. So whoever's the stronger of the two, either the acid or the base, then that's where your pH is going to lie. Now, what pH am I talking about? I am talking about the pH at our equivalence point. That's a new word. And you're like, what is an equivalence point? You're about to find out. Okay. So when I'm talking about these pHs, it's going to be at this equivalence point. Equivalence point we'll talk about in just a second. Okay. When we'll look at it graphically, and it'll help kind of get a visualization for what's going on. But I don't want to jump too much into that. Acids and bases is a lot. There's a lot of information here. And so we're just really in AP chemistry. We just really barely just get started on it. Okay. So again, this is the setup. This is a great picture. This is a setup of a titration where we have the flask and we have our analyte is in the flask. And then up here we have our titrant. And that's the one that we know the concentration of. Okay? So that's the basic vocabulary just to kind of get everybody caught up to where we are before we jump into this. Okay. Now, titration of strong acid and a strong base. So we just saw that one. Okay? Don't forget, acid plus base yields salt plus water. In this particular case, we have a strong acid where HCl is being titrated with NaOH. And the NaOH, and this is a strong acid, and this is a strong base. And they have a pH at the equivalence point that is equal to 7. And you can see the equivalence point is noted here. And we're going to look at this graph and talk through it, okay? So this is the point at which we have equal moles of both the strong acid and the strong base. This is what I want you to know about the equivalence point. At an equivalence point, at the equivalence point, this is where we have our moles of acid equal to our moles of base. The equivalence point is important to us. So I want you to think about this, and I want you to go back to this picture real quick. Look here. Now, typically we'll have a pH meter, and it's measuring the pH of the solution. And the pH meter does not go into the burette. The pH meter goes into here. So I have a pH meter that's constantly reading the pH inside a flask or a beaker. Sometimes we'll use a beaker because it's easier to get the pH meter in there, but we have some way that we are constantly measuring the pH. Okay, so here, if you look when I first start, that means at the initial time, my pH is really low. It's like around 1. So that tells me that this is acidic. Actually, it tells me that it's a strong acid, and I'll tell you how you know that in just a second. But we have an acid, that's why the pH is low. And then what's happening is I'm adding from the burette, I'm dropping in some base. And then the pH is on the rise because it's going to approach becoming basic. And then all of a sudden, you'll see this massive jump. This really, 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 really steep point. It's called the inflection point. Just like you use inflection, we use that word in the English language to talk about inflection and tone in our voice. So the inflection point is where you have this big jump. And so you have this massive, like vertical leap in the pH, because that's what's on your y-axis. And then all of a sudden it starts to become super, super, super basic. And so what's initially happening in this titration is I've got a whole lot of H pluses. And then I'm dropping in from the burette, the OH minuses are dropping in, right? And they're dropping in, and what happens with OH minus and H plus? They make water. But I still have a lot of H pluses down here. And then as the OH minuses are coming in and reacting with those H pluses and removing them and making H2O, the pH is slowly on the rise. We get to this thing called the equivalence point, and that's where the OHs have equaled the number of H pluses. So all of the H pluses are now gone, and there's no H pluses floating around in that solution, and there shouldn't be any OH minuses floating around in that solution either. If you added one more drop of the OH minus, then you now are further up you're above the equivalence point. All right, so H pluses are in the solution down here, and we're dropping in OH minus, OH minus, OH minus, and they're making water over and over and over again. And then all of a sudden there's this massive jump in the pH. And so when we see this massive jump in the pH, because we had measured the pH here, and then after the next drop, I'd be highly unlikely that you got it measured exactly at the equivalence point. You usually have to estimate that spot. And then usually the next drop, you're up here. And then so you have this huge inflection point where it's massive. And what you do is you find this vertical part of the graph and you find the halfway point. And the halfway point between in that vertical region, that is where your equivalence point is. And then you follow it over and you're like, oh, okay, the pH at the equivalence point was 7. Okay. Now with the pH being 7, that tells you that this is a strong acid and a strong base. That's number 1. All right, so let's go back to our bullet points, and I'm going to keep talking because titration curves are big on the AP exam, and we want to make sure that we can talk about them and understand them. All right, so the third bullet point, the inflection point, which is your steepest point in the graph, super large steep slope, corresponds to the equivalence point. So halfway between, okay, so you have the top and the bottom where it's vertical, halfway between is your equivalence point. So if we have the volume of sodium hydroxide, which is your NaOH, where do we have the volume from? Right here on our x-axis. And we know its concentration. Then we can use it to calculate the molarity of the acid. How can we do that? Because we know how much acid we added into the flask. Okay, so click back over to our picture. This volume of the acid, the molarity is unknown, but we measured the volume. Okay, so our volume was measured, so we know it's however many milliliters it is. So we know the volume of the acid, we don't know the concentration. And so we're dropping in this base through this burette, and then what's happening is we're measuring the pH, and the H plus is reacting with the OH minus and making water, and reacting and making water, and reacting and making water, and all of a sudden our pH shoots up really, really high. Now, in this picture they show, and the other thing that was in the video, indicators are great. So indicators are not as accurate as a pH meter, but the indicators will show you a color change. And they'll show you that color change as the pH is changing. You'll start to see flashes of color, and then the color will turn. It's lots of different colors. It depends on which indicator you use. How do you know which indicator you use? You use an indicator depending on which acids and bases you're working with. IP actually used to ask very specific questions about that, but they really don't anymore. So we're not going to get into all that because acids and bases can be tough. It's a lot of information. All right, so strong acid, strong base. Now, how do I know that I started with a strong acid? All right, well, here's the deal. Remember the pH range is 0 to 14, right? All right, so 0 to 14. If my pH that I start with is either in the top 2 or the bottom 2 on the pH scale, so between 0 and 2 or 12 and 14, then I'm dealing with strong. So strong what? Well, it depends on where you are. So if I'm down here between 0 and 2, that means a strong acid. If I had started up here at like 13, then that means that's the strong base range. And the same is true for where you end. So when my pH ends somewhere between 12 and 14, then that means that whatever, in this case, that what I titrated with was also a strong base. And then if the opposite could be true, if the curve was down here and I had a strong acid and I ended somewhere between 0 and 12. So that's an indicator. And then if you had this other range that you started in between, let's say above 7 but below 12, then that means you had a weak base. Or if you were below 7 and above 2, then that means you had a weak acid. Okay, so that's one way you can figure out where you're at and what type of acid and base you're working with by just looking at the graph. Because sometimes with titrations, they give you word problems, they give you math, or they give you the graph. And they really like the graph because y'all don't like graphs, but you have to learn to like them because this one pops up a lot on the AP exam, okay? It's a big one. This is big AP stuff, okay? All right, so now when we have a titration of a weak acid and a strong base. So remember what's sketched right here was like what we just had. Okay, so what we had just a second ago. So we had HCl, which was a strong acid, and then we had NaOH, which was a strong base. Now we still have the NaOH, but for the one with the black line, the solid black line, instead of having a strong acid, we had a weak acid. And you know it's a weak acid from the starting pH because it looks like it's starting at around 3, which is above 2. It's still acidic because it's less than 7, right? But it's above 2, which means it was a weak acid. So we're still going to evaluate the steepest part of the curve, where right here, this inflection point, and go to the halfway mark, which is about here. Okay. Now notice that's really the steep part of the graph isn't quite as steep as it was on the last one. Why? Because we'll take a look. I mean, if we started down here and we go all the way up, that's a much larger range. But in this particular case, we're starting here and we're going up. So that inflection point isn't as wide when you're dealing with something being weak. It could be acid or base. When one of them is weak, you won't see such a big inflection point. So that's one thing. And then I also can tell that, so I know I'm starting with a weak acid, and I can tell that I'm starting with a stronger base because my pH is above 7. The equivalence point is somewhere around 9. I drew my line kind of crooked, but the pH at the equivalence point is somewhere around 9. And remember, equivalence point, moles of acid equals moles of base. That's so important. Okay? Now the other thing that they like to do, besides have you interpret these graphs, is they like to have you draw them. It's actually big points on drawing on the titration curves on the AP exam. Big points. Okay, and so we'll talk about it. I mean, 2 to 3 points is massive. Okay, so on this particular graph, I'm taking a look at it and I am trying to decide where I'm at. So I see that right here, I am starting at above 2. So I'm going to say, okay, I have some kind of weak acid. I know it's a weak acid. I'm starting above 2, and I can tell by looking at the curve. And we're going to talk about that. And then for the base, I'm taking a look at this and I'm like, you see how down here or up here at the end, I am ending above 12. So this looks like a strong base to me. Okay. You see it? Now, one thing I haven't talked to you about is something called a buffer. So let's get out of here for just a second and come back over here for just a minute. All right, so let's talk about a buffer solution. And we're going to look back at the graphs in just a second. But let's define a buffer solution, and then we'll look at a graph and figure out how to tell if it's a buffer or not. Okay, well, what is a buffer in the first place? Well, a buffer sort of is something that kind of slows something down. It calms something down. So, you know, sometimes if you have to go talk to your parents about something you don't want to talk to them about, and you know, you maybe take somebody with you, or you have some type of support system set up so you can kind of calm things down and maybe not have such a dramatic response. And it's similar in this in titrations, because you remember we don't see such a dramatic change. So buffers kind of calm things down, and graphically I'll show you how to tell if you where that buffer region is and how you can see it. But when you have a buffer, by definition, you either have a weak acid or a weak base, either or. One of them has to be weak. And it's salt. This is important. I've seen this a lot on multiple choice, like which of the following is a buffer solution? And that's like the prompt, and then they'll give you like the answer choices and you have to pick. Okay, well, let's say I had, this is the most loved weak acid for AP, so it's acetic acid. Say I have this one. And then let's say I have this weak base. NH3 is also equally popular. All right, so this one's super popular. He's a popular weak base. So I have a weak acid and a weak base. So if I wanted to know, is this a buffer solution? And the answer is no. I have a weak acid and I have a weak base. That's not a buffer solution. No, because in order to be a buffer, I have to be one or the other, and it's salt. What the heck is a salt? Remember, salt is an ionic compound, right? So let's take a look at another equation. Let's take acetic acid and let's put it with NaOH. Remember, I told you these are double replacement reactions, right? And so what are they going to do? They're going to switchy swap their partners. So I have my H plus, which is a cation, and my Na plus, which is a cation. And then I have my acetate, which is my anion, and my OH minus, which is my anion. So they're going to flippy flop their partners. And so I'm going to end up with Na, C2, H3, O2, that's my salt, plus H2O. I have an acid plus a base gives me salt plus water. Okay, so now if I just have these two, like right before I mix them together, is this a buffer solution? And the answer is no, it's an acid and a base. However, if I have this, I don't know if I want to say plus, let's just say, because they usually just give you a list of what's happening and who's present. These two things. Is that a buffer? And the answer is yes, that is a buffer solution. Why is this a buffer solution? Because this is a weak acid and this is its salt. Where's the its? Apostrophe S, because it's possessive. That's its salt. How do you know it's salt? Because it's its anion. It's the same one. So how about this one? What if I give you this? What if I give you this right here? Weak acid and NaCl. Well, is NaCl a salt? Yes, NaCl is a salt. We know that. Is it its salt? And the answer is no. So this one, not a buffer. This one, yes, it's a buffer. Why? Because it's a weak acid and it's salt. Are these two, just those two together, a buffer? No, that's an acid and a base. Are these two together a buffer? And the answer is no, it's just an acid and a base. So they will like to give you something like this. How about this? Is this a buffer? No. Why? Because this is a strong acid and it's salt. So this is his salt, yes, but this is a strong acid. Strong acids don't have buffers. Weak acid or a weak base and it's salt. You've got to make sure you keep those straight. It says easy points, but you've got to keep that straight in your head. And I'm going to tell you, this is on the AP exam. I'm telling you, it's going to be on there. All right, so let's go back over here and we're going to look at our curves. And I actually want to go, I'm on the pen. I'm going to go back for a second to this one. Let's talk about the curves. Remember I said you can see the buffer in action because the buffer slows things down. It calms it down. Okay? So with my strong acid right here, My pH is slowly on the rise. You can see how it's just sort of like level, it's sort of like level on the rise. And then it's like inflection. Okay, you see that strong. Now weak. You notice how the slope is kind of goes up pretty quick, and then it kind of slows down, calms down a little bit. It calms down. And so right here where it calms down, this is your buffer region. And so when you're looking at the graphs, it's really good. And if they ask you to draw it, they're looking for this. What are they looking for? Well, if you have a strong acid, they're looking for a steady increase, steady, slow increase, and then a huge inflection point. Okay, and then a steady, slow tapering off, and make sure your starting and ending pHs are in the right place depending on who's the acid and who's the base. Okay, if they give you a weak acid, like in this picture, they want to see the slope a little bit steeper for like a very short amount of time, then it tapers off. So you're graphically showing that there's a buffer region. So it goes, ooh, okay. So it's like, oh, pH increase, and then it levels out. Why? Buffer region. Because the salt is there. It's salt. The weak acid's salt. And then inflection point. And so inflection point, not quite as big. It's a little smaller than if it were a strong acid. And then tapers off. And then make sure your ending pH is in the right space, okay? All right, we're going to keep working on this because this is big. Now, here, let's come back to this diagram. Now notice these sort of like gray looking, is indicating different points on the graph. All right, so this is at the start. So at the start, right here, I have, oh, that was not supposed to happen. Okay, back. I have just my acid. So this is acetic acid. So it's the same acid. They wrote it as an organic molecule with this one, even though we're not supposed to have to do organic things in AP chemistry. They do sometimes like to write acetic acid this way. They're the same thing. Okay, they're the same thing. So this is before you start. This is at 0 milliliters of NaOH have been added. You have your starting pH. It's above 2, not quite 3. It looks like it's almost a 3, but not quite there. All right, so there's nothing in the solution. Then we look at the second region. This is my buffer region. All right, why is this the buffer? Okay, well, this, I still have some acid. And these are my molecules are a little bit hard to identify, but take a look where I have the black dot is the carbon, and then it has 3 hydrogens on it. And then I have another carbon, and I have 2 oxygens on it. And then you see that H right there? Clear it. This H right here, this H right here, this H right here, that's the acidic H. Okay, so that's this H right there. Or if you wrote it out like this, like an ionic compound, it's this H here. So that H is donating, it's coming off. All right, and then it's going to go and be with the OH from the NaOH and make water. All right, and then so what's floating around in the solution is I have the acid is in the solution. I have the Na plus is in the solution. That's from the sodium hydroxide. And then this is the acetate. Notice that white, that this is missing off of the acetate ion. Okay, so what's happening and what's in my solution right here? I have some acetic acid, but then I have the salt. So I have a weak acid and it's salt. This is my buffer solution. I've created the buffer solution, and this is what they call the buffer region of the graph. But this is my buffer solution, and that's where your graph starts to level out, calm down just a little bit. Crazy pH, calm down. Okay? The buffer calmed it down. Keep it straight. This is tough. I know it. All right. Actually, we all have those things. Like sometimes there's some units that you just don't click with. Sometimes they're within a unit, you're like okay with most of it, but then there's like one thing you don't quite get. I get you. If acid bases are not your thing, I follow you. This was for me. I hated acid-base chemistry. Hated it. Until I was in my 3rd chemistry class in college. Then, one day, I don't even know what the professor said. It was some professor. His name was Dr. Avincula. He was really nice, though. He was really good. But he was up talking, and he just said something, and it wasn't even anything major. But he said it, and then all of a sudden, I had that moment where everything I had learned, the 2 previous chemistry classes I had taken for acids and bases, I was like, oh, okay, I get it now. So you have those moments. Acids-based chemistry was for my first couple of chemistry classes. I had such a hard time grasping it. So if this one's hard for you, I feel you. Okay, I feel you. That's why I'm trying to just ease into it. We can always have conversations about it in class and stuff. Okay, so now this third area is the acid has been completely neutralized. You notice there's no acids floating around. So remember the little white dot here is the acidic proton. It's all gone. All I have is the acetate ion, and I have some Na+. There's no acetate. Nope, that's not true. There's no more acid, and there's no more OH-. There's none. It's all gone. So this is the equivalence point. So we're right here at this equivalence point where there's no H+, no OH- floating around. All I have is the salt and the water. At the equivalence point, moles of acid equals moles of base, and when they equal to each other, they make water. And the only thing that's left right there is water and salt. Okay? And I'm taking a look at this one. The pH is greater than 7. It's like 8 something. And then, so that tells me, that confirms for me that this is a strong base. Okay? And we talked about why that's a weak acid. All right, and then we keep adding. We keep adding from the burette, the NaOH into the acid. We're adding, and then the pH is getting higher and higher and higher and higher and higher, and above 12 since it's a strong base. And then we're at this last part where there's definitely no acid left to react with that OH- that's floating around in there. So now we just have OHs floating around, and so the pH is just getting higher and higher and higher and higher and higher. Okay? So, that's a lot. I get it. I get it. Titrations are hard. Kids don't like titrations. It doesn't matter if you do the lab in class or not. Honestly, it doesn't matter. They still are hard. Okay, so freeze. We have the equivalence point. And the equivalence point is the halfway point if you are dealing with of the inflection point. And this is about the halfway point if you're dealing with this weak acid, a strong base. Now, all of these that we've looked at so far are starting with the acid being the unknown concentration in the flask and the base in the burette. It doesn't have to be that way. It can be the other way around. And your starting points would be up here somewhere. And we're going to see those graphs in just a second. But there is importance in another thing called a midpoint. I know it's a lot of vocabulary, right? We had the analyte, we had the titrant. Analyte was what we're analyzing. It's in the flask. The titrant, that's what's in the burette. And then we had the equivalence point. That's halfway between the inflection point. And it is moles of acid equals moles of base. There's no H+, no OH- floating around. Now, there's another vocabulary word. I know, sorry. Midpoint. Okay, the midpoint of a weak acid. Weak acid or a weak base. Weak. Not strong. Weak and weak only. Weak acid, the midpoint between a weak acid and a weak base in a titration is halfway between the starting point and the equivalence point. So what that means is this is where we started and this is our equivalence point. At the equivalence point, we added 40 milliliters of our base. What's halfway between 0 and 40? 20. So it's halfway there. So wherever the equivalence point is, halfway from where we started to when we got there, that's the midpoint. Okay? And so at 20 milliliters, that's our midpoint. And we can find the pH at 20 milliliters, and that helps us figure something out. And so what that's telling us is the significance of this is actually incredibly significant. And so this is the type of, this right here, this slide and this information is the stuff that's going to make the difference between those of you that are going to get 4s and 5s on the AP exam. So if you're like, your mind is blown right this second, just skip forward a couple, just go to the next slide. And if you're like, okay, I'm going to try and hang in there, then hang in here and listen. But let's go, okay? So the midpoint for this one is at 20 milliliters. It's extremely significant for us. It's really important because half of our acid has reacted, half of it at this point. So what we can do, if the acid has reacted, then that means that when it reacts, it donates the proton. So we have the conjugate or the anion, right? So I'm trying to make sure I have room to write. So if I have my acid, then I have its conjugate base, right? Because acid donates a proton. So this is my acid and this is my conjugate base. Ooh, that's supposed to be a C. My conjugate base. So if it's halfway through reacting, if half of this has reacted, then that means that the concentration of my acid is equal to the conjugation, the concentration of my conjugate base. They're equal to each other. Because if I had 100 molecules of acid and half of them had reacted, then that means I have 50 acids left and 50 conjugate bases now. Okay? So, lovely. Now, if those two are equal to each other, there's this lovely equation called the Henderson-Hasselbalch. Coming up soon, different video, not today, but in this video. In this equation, we have the pH equals the pKa plus the log of the concentration of the base divided by the concentration of the acid. Okay, lovely. You're like, I hate that equation. I got you, it's okay. But listen, here's the deal. If this is my acid and this is the conjugate base, when I plug them in here and they're equal to each other, that means that that ratio is 1. And the log of 1, put it in your calculator. If you don't believe me, the log of 1 is equal to 0. Okay. Concentration of the acid and the concentration of the base at the midpoint are the same because half of my acid has reacted. So I have half of my acid, and then the other half that reacted turned into my conjugate base. That ratio, their concentrations are the same, and when I divide them, they equal 1. And when I take the log of 1, based upon that formula, the log of 1 is 0. So what that means is that the pH is equal to the pKa. So for this particular thing, pH equals the pKa, well, let's say the pH is 5. So 5 equals the pKa. Well, now I can solve for the Ka, and the Ka for this one would be 10 to the negative 5. Or you could say 1 times 10 to the negative 5, it doesn't matter. You can use this to identify which weak acid you have. Because if you, I should have written the A, sorry. That's your Ka because it's an acid. It'd be a B if this were the opposite. But you can use this Ka to identify, so they'll give you a list. They'll say, these are your possible acids, these are their Ka values. How do you know which one it is? That's how you know. Okay, that's big. This is big. You're going to need to absorb, you're going to need to think about this. You're going to have to come back and listen to this a couple times because that's big. Okay, now they love to have you analyze graphs. So these are some graphs that you can see, and the analysis is underneath. So it's already done for you. All right, so just kind of, there's a lot of information. So let's just look at A. So notice in A that we are starting down here at like pretty much 0, which is a really strong acid, right? And then look at where the ending point is up above 12. So that's a strong acid and a strong base. All right. So it could be HCl and NaOH or whatever. How do I know this again? Because it starts with a pH less than 1. That's because it's 100% ionization of the acid. The pH changes very slowly. So it's a very level, it doesn't have that quick jump at the beginning. It's just pretty level. The pH change is kind of slow. And then then all of a sudden, boom, at the inflection point. So it has a large region of the pH change at that inflection point. It's really large. And it jumps like 8, because it's like around the pH of 2 up to around the pH of like 9 or so, or I don't know. It's a huge range. So the range is massive, and the equivalence point has a pH of 7. So I know that this one in my flask was a strong acid. And then the burette, there's not room. The burette was a strong base. I know that just by looking at this. All right, then if I look at this next one, all right, I'm noticing that I have a weak acid in my flask. And then I have a strong base in the burette. How do I know that? Because where I'm ending. pH is above 12. Okay, so let's take a look. So we have a pH that is starting above, 3 or above, so it's above 2. So less ionization or dissociation of the acid. The pH change is rapid at first, and then it levels out because it's a buffer. Rapid buffer. Okay, so that's important. This range at the equivalence point is smaller than this one. And that's also an indication that you're dealing with a weak substance. And the equivalence point is greater than 7, which is my other indicator that this makes this a strong base. Okay? The base is stronger than the acid. Could be a weak, no. Ignore where it ended. Okay? If it ended like at around 11, then it could have been a weak base. It should have been a weak base, but then the Kb value, and you compared the Ka and the Kb value for the base would have been greater than the Kb value for the or the Ka value for the acid. But in this case, it doesn't. It ends above 12, so it's a strong base. Okay, so now C, weak base. All right, so take a look. This one, we haven't looked at one of these yet. So notice we're starting with the base. So that means in my flask is a weak base. And then I'm looking at my acid. Hold on, I'm sorry. That's my daughter in college. I'm trying, she keeps calling. Okay, so back to this. Weak base is in my flask. So I know it's a weak base. Why? Because look at my starting point. Number one, the pH is starting at around 11. So I know it's base. I know it's a weak base because it's less than 12. And then also you see how the slope is steeper and then it levels out. Steep. And then the buffer happened. Why? What's the buffer? It's because it was a weak base and its salt is in that buffer region. Here's your buffer region right here. Okay, so the pH is around 11. The pH changes rapidly at first and then slows down. Buffer. All right, it has a smaller inflection zone. And then when I'm looking at the equivalence point, the pH is around, it's less than 7 for sure. It looks like the pH at the equivalence point is around maybe 5-ish. And so that tells me that the acid is stronger than the base in this particular one. And this one has to be a strong acid. Not just a weak acid that has a stronger Ka value, but it has to be a strong acid because that's in the burette, because the ending point pH is between 0 and 2. Okay. Now, D. We have a strong base in this one. How do I know? Well, look at that. I start above 12. It's just a really slight gradual change in the pH. Pretty big inflection point right there. Halfway point, it looks to be around 7. When I'm looking on my iPad, it's way smaller than looking at it up on the big screen. I can't really see it. Somewhere around in there, a little higher. But that's about the halfway point. So the pH is around 7. So this was a strong acid, strong base. But the difference is in this particular one, we started with the base. The base was in the flask, and it was my unknown concentration. And I had a strong acid was in the burette. Burette was a strong acid. Okay. So they're going to have you analyze these graphs in multiple choice. Easy. They're going to be like, give you a bunch of graphs and you got to pick out which one is which. There you go. They can ask you to draw. Be able, on the short answer, be able to draw these. Be able to have those points. They're looking for the strongs to have pretty level changes, for the weaks to have a little bit of a start jump, and then they level out because of the buffer. They're looking for where's the equivalence point. Where do you start and where do you end? All of that matters. It's not hard, but it matters. Okay. So I'm not going to spend a lot of time on this slide. They don't do this on the AP exam anymore. This is polyprotic acid. So like H2SO3 or anything, or H2SO4 or whatever, it doesn't matter. So a titration curve, if it's a polyprotic acid, if it has more than one acidic proton, you're going to have 2 inflection points. Oops, I need my pen. 2 inflection points. That's it. Notice the inflection point of the second one is smaller than the inflection point of the first one. Well, of course it is. You give off one of your protons the first time, then your conjugate base, it can still be acidic, even though it's base. It can still be acidic, though, if it has an acidic proton, like this one. Okay. So this guy is amphiprotic. He can act as an acid or a base. But he's not as strong of an acid. He's a much weaker acid. This is a much weaker acid than that. So his inflection point is smaller. Okay, not going to talk any more about that. Moving on. All right, so let's do our problem and then we're done. Because this is a lot for one day. I'm telling you, titrations and acid-based stuff is hard. I got you. And if you're understanding it, it's because I'm explaining it so well. Okay, so given the strong acid, strong base titration curve shown to the right, estimate the equivalence point and determine the concentration of the HCl if you are titrating 20 mils of HCl with 0.121 molar NaOH. Okay, let's figure out the equivalence point, which they got the little dot right there to help us. So the equivalence point is right there. So the pH of the equivalence point is around 7, which is further proof that this is strong acid, strong base. I know it's strong acid, strong base because they gave me those, but then I also know I'm starting between 0 and 2. I'm ending above 12, between 12 and 14. The equivalence point pH is 7. I mean, it's just beautiful. It's all lining up nicely. All right, so what they want me to do is figure out the unknown concentration of the HCl. My favorite formula for this is M1V1 equals M2V2. Now, if you're following along with also your note set, you will see that the note set is using a stoichiometry method to solve this. And you can totally do that if stoichiometry is your jam. Normally stoichiometry is my jam because I love it, but this is so much easier. Actually, you know what? I'll work it over here so we can have them side by side. All right, so totally so much easier. All right, so right there. Now, M1V1, M2V2. So yes, it's our boom boom equation if we're diluting. So pick one to be the acid, one to be the base. Who cares? Doesn't matter which one's which. I'm solving for this. This is my unknown. All right, so I'm going to solve for the molarity of the acid. So I need to know the volume of the acid. Well, I'm starting with 20 milliliters of HCl. All right, great. Now I need the molarity of the base. Well, there it is. 0.121. That's my molarity. And I need the volume of the base. They didn't tell me. Yes, they did. Look at the graph. It's on the graph. At the equivalence point. That's where my moles of acid equal my moles of base. That's the only time this is going to work. All right, so this formula doesn't work any other time. It has to be at the equivalence point. That's where they're equal to each other. So I need my volume here, and my volume halfway between 20 and 30 mils is going to be 25. Okay, so now we do our math. So I'm at home, so my calculator is not the best one, so let me make sure. Okay, so my calculator says this. That's what it says. All right, and so that is my molarity of my acid. So now I need to give my answer. And this one's good. This is a good one for them to kid you on sig figs if this is a sig fig question. All right, why? Well, there are 3 sig figs here and there are 3 sig figs there. You will notice this answer only has 2. Why? Well, there's another number. Oh. This is an analog reading. So we estimate one spot. We estimated. All right. So there are 2 sig figs here. The markings are at 20 and 30. So we estimate the one spot. So the 25, the 5 is in the one spot, 2 sig figs on this answer. So 0.15 molar HCl is the answer. And actually, if you added 3, you would be plus or minus 1, so you would be okay anyway. But they would like you a lot if you recognize that. That's extra special. Okay, that's it. We're done. Have a great day.